Before we get started, don't forget to hit that subscribe button and ring the notification bell so you never miss out on our latest training content. And if you find this video helpful, give it a thumbs up, it really makes a difference. In today's video, we are diving into 8 rule of SPC means Statistical Process Control. We'll cover everything in details, and by the end of this training, you'll have a solid understanding how to analyze control chart. So let's start 8 rules of SPC. Statistical Process Control, SPC, is a method used in manufacturing and other industries to monitor and control processes. While there are more than 8 rules associated with SPC, one common set of guidelines is often referred to as the 8 rules of SPC or 8 Western Electric rules. These rules are used to identify patterns and signals of special cause variation in a control chart, indicating when a process may be out of control. If you want to interpret any control chart, then draw few lines in the control chart for detailed analysis as per below. First, draw or highlight X bar or mean line in the control chart. Then draw a line 1 sigma distance from X bar or mean line in both upper side and lower side. This area is called as Zone C, means you can say, Zone C is the zone closest to the average. It represents the area from the average to 1 sigma above the average. There is a corresponding zone C below the average. Then draw another 2 lines, 2 sigma distance from X bar or mean line in both upper and lower side. Highlight the area in between 1 sigma line and 2 sigma line. This area is called as Zone B. You will find there is a corresponding Zone B below the average line also. Then draw another 2 lines, 3 sigma distance from X bar or mean line in both upper and lower side. Highlight the area in between 2 sigma line and 3 sigma line. This area is called as Zone A. You will find there is a corresponding Zone B above and below the average line also. Lastly, highlight all areas above and below the 3 sigma line from X bar or mean line is called as rejected area or zone. After defining the 3 zones in the control chart, you have followed the 8 rules of SPC to find any conclusion for improvement or to take actions for process strengthening. Next, let's see each rules one by one. First rule is 1 or more points beyond the control limits. This is also called as beyond limits rule. Second rule is 2 out of 3 consecutive points in Zone A or beyond. This is also called as Zone A rule. Third rule is 4 out of 5 consecutive points in Zone B or beyond. This is also called as Zone B rule. Fourth rule is 6 or more consecutive points on one side of the average in Zone C or beyond. This is also called as Zone C rule. Fifth rule is 6 consecutive points trending up or trending down. This is also called as trend rule. Sixth rule is 8 consecutive points with no points in Zone C. This is also called as mixture rule. Seventh rule is 15 consecutive points in Zone C. This is also called as stratification rule. Eighth rule is 14 consecutive points alternating up and down. This is also called as over control rule. Next, this how all 8 critical patterns look like in any control chart. Rule 1 is if 1 or more points beyond the control limits. Rule 2 is if 2 out of 3 consecutive points in Zone A or beyond. Rule 3 if 4 out of 5 consecutive points in Zone B or beyond. Rule 4 if 6 or more consecutive points on one side of the average in Zone C or beyond. Rule 5. If 6 or more consecutive points trending up or trending down. Rule 6. If 6 or more consecutive points with no points in Zone C. Rule 7. If 15 consecutive points in Zone C. Rule 8. If 14 consecutive points alternating up and down. Analyzing a control chart for special cause variation can be facilitated by using the categories used with a cause and effect diagram. The following are the categories that I prefer to use: equipment, machines, and tooling; environment, process, inspection, materials, operator. Next, as discussed, rule number 1 says, if one point beyond the three control limits seeks to identify points that are random or outliers, as shown here in red. When random or outlier points are identified, the following are potential special causes to consider: equipment, machines, and tooling; improper startup, improper setup, sudden support system failure, cooling, heating, compressed air, vacuum, steam, etc. Tool failure or breakage, equipment or machine failure, improper equipment, machine, and tooling maintenance, utility interruption, environment, temperature suddenly too low or high, humidity suddenly too low or high, process, equipment has not stabilized, warmed up, inadequate work instructions, missed process step, new process, inspection, measuring, and testing equipment not properly calibrated, damaged inspection, measuring, and testing equipment, materials, change in raw materials, change in components, handling damage, expired materials, operator, new operators, inadequate training, operator interrupted or distracted, operator overcompensating when making process adjustments. Rule 2. If 2 out of 3 points in Zone A is considered a large shift, the shift can be on either side of the center line. The points circled in red are considered large shifts. When a large shift is identified, the following are potential special causes to consider: equipment, machines, and tooling; improper setup, support system failure, cooling, heating, compressed air, vacuum, steam, etc. improper equipment, machine, and tooling maintenance; environment, temperature suddenly too low or high, humidity suddenly too low or high, process, new process parameters, incorrect process parameters, process has degraded, inspection, measuring, and testing equipment not properly calibrated, inspection, measuring, and testing equipment not adequate for the intended use, damaged inspection, measuring, and testing equipment, materials, mixed raw materials, mixed components, operator. Next, Rule 3. If 4 out of 5 points in Zone B or beyond is considered a small shift, the shift can be on either side of the center line. The points circled in red are considered small shifts. When a small shift is identified, the following are potential special causes to consider: equipment, machines, and tooling; improper setup, intermittent support system failure, cooling, heating, compressed air, vacuum, steam, etc. improper equipment, machine, and tooling maintenance; environment, temperature suddenly too low or high, humidity suddenly too low or high, process, New process parameters. Incorrect process parameters. Process has improved. Process has degraded. Inspection. Inspection, measuring, and testing equipment not properly calibrated. Inspection, measuring, and testing equipment not adequate for the intended use. Damaged inspection, measuring, and testing equipment. Materials. Mixed raw materials. Mixed components. Operator. New operators. Inadequate training. Operator interrupted or distracted. Shift change. Next. Rule 4. If 6 or more points on one side of the center line without crossing is considered a prominent shift, the shift can be on either side of the center line. The points circled in red are considered a prominent shift. When a prominent shift is identified, the following are potential special causes to consider. Equipment, machines, and tooling. Improper setup. Improper equipment, machine, and tooling maintenance. Damaged tooling. Tool wear. Environment. Temperature shifted to low or high. Humidity shifted to low or high. Process. New process parameters. Incorrect process parameters. Process has improved. Process has degraded. Inspection. Inspection, measuring, and testing equipment not properly calibrated. Damaged inspection, measuring, and testing equipment. Materials. Change in raw materials. Change in components. Expired materials. Operator. New operators. Inadequate training. Operator interrupted or distracted. Shift change. Next. Rule 5. If 6 points or more in a row steadily increasing or decreasing is considered a trend, the trend can be rising or falling. The points circled in red are considered a trend. When a trend is identified, the following are potential special causes to consider. Equipment, machines, and tooling. Gradual support system failure, cooling, heating, compressed air, vacuum, steam, etc. Tool wear. Environment. Temperature gradually drifting to low or high. Humidity gradually drifting to low or high. Process. Process is slowly degrading. Inspection. Inspection, measuring, and testing equipment not adequate for the intended use. Damaged inspection, measuring, and testing equipment. Materials. Variation in the raw materials. Variation in the components. Operator. Operator distracted. Next, Rule 6. If 6 or more consecutive points with no points in Zone C, the Statistical Process Control (SPC) rule you are referring to is often associated with control charts and is related to the presence of consecutive data points outside Zone C. This rule helps identify potential patterns or trends in the data that may indicate special cause variation in the process. When you have a control chart with consecutive data points falling outside Zone C, either above or below the center line, for 6 or more consecutive points, it suggests a potential shift or trend in the process. Interpretation. Consecutive points outside Zone C. This part of the rule focuses on the consecutive nature of the points. If the points are consistently above or below the center line for an extended period, it indicates a potential shift in the process mean. No points in Zone C. The absence of points within Zone C during this consecutive run suggests that the process is not fluctuating within a normal range. The lack of points in Zone C implies that the process is exhibiting a sustained shift rather than random variability. Possible causes. First may be due to process shift. The most common interpretation is that the process has undergone a significant shift. This could be due to changes in equipment, materials, operating procedures, or other factors influencing the process. Systematic changes. There may be systematic changes affecting the process, leading to a sustained trend in one direction. Action steps are: first, investigation. When this rule is triggered, it's essential to investigate the potential causes of the sustained trend. Look into recent changes in the process, equipment, personnel, or other relevant factors. Second, correction. If a significant shift is identified and deemed undesirable, corrective actions should be taken to bring the process back into control. This might involve identifying and rectifying the root cause of the shift. Third, update control limits. Depending on the findings, it may be necessary to update the control limits on the control chart to reflect the new state of the process. Next, SPC Rule 7. When you observe 15 consecutive points falling within Zone C on a control chart, it suggests that the process is exhibiting stability. Zone C is typically the region within the control chart that is close to the center line and signifies that the process is in statistical control. Equipment, machines, and tooling. Check if there have been any recent changes or maintenance activities related to equipment, machines, or tooling. Stability in Zone C may indicate that these elements are performing consistently. Environment. Assess whether any changes in the environment, such as temperature, humidity, or other external factors, might be influencing the process. Process. Examine the overall process for changes or improvements. If the process has been modified, it could explain the observed stability in Zone C. Inspection. Review the inspection procedures and criteria. Consistency in inspection methods may contribute to the stability observed in the control chart. Materials. Analyze the materials used in the process. Consistency in material quality and characteristics may contribute to the stability of the process. Operator. Evaluate the role of operators in the process. Rule 8. If 14 points in a row alternating up and down is generally considered to be over control. The points enclosed in red are considered out of control. When this situation is identified, the following are potential special causes to consider. Equipment, machines, and tooling. Improper setup. Intermittent support system failure, cooling, heating, compressed air, vacuum, steam, etc. Improper equipment, machine, and tooling maintenance. Environment. Temperature intermittently too low or high. Humidity intermittently too low or high. Process. Equipment has not stabilized, warmed up. New process parameters. Incorrect process parameters. Inadequate work instructions. Missed process step. New process. Inspection. Inspection, measuring, and testing equipment not adequate for the intended use. Damaged inspection, measuring, and testing equipment. Materials. Mixed raw materials. Mixed components. Operator. New operators. Inadequate training. Operator overcompensating when making process adjustments. Operator not waiting for the process to stabilize before making process adjustments. Please note, even though the operator may be over-adjusting the process, there may be other special causes present. Next, if we summarize, Then rule 1 and 2 indicates large shifts from the average. Then rule 3 and 4 indicates small shifts from the average. Then rule 5 indicates trends. Then rule 6 indicates mixtures. Then rule 7 indicates stratifications. Then rule 8 indicates over control of process. Next, if we summarize the cases of patterns present in a process as per SPC rules, then rule 1 and 2, which is focuses on large shifts from the average. And the possible causes are: new person doing the job, wrong setup, measurement error, process step skipped, process step not completed, power failure, equipment breakdown. Rule 3 and 4 focuses on small shifts from the average, and the possible causes are: raw material change, change in work instruction, different measurement device or calibration, different shift, person gains greater skills in doing the job, change in maintenance program, change in setup procedure. Next, rule 5 describes trend, and the possible causes are: tooling wear, temperature effects, cooling, heating. Rule 6 describes mixture, and the possible causes are: more than one process present, such as shifts, machines, raw material. Rule 7 describes stratification, and the possible causes are: more than one process present, such as shifts, machines, raw materials. Rule 8 describes over control of process, and the possible causes are: tampering by operator, alternating raw materials. Next, implementation steps of statistical process control. While SPC can help control processes and ensure consistent output, many of China's factories seldom apply it. To understand how this tool works, it is best to follow the logical steps in its implementation in a factory. Select critical to quality (CTQ) product characteristics. For example, if the metal hardness is lower than expected on a screwdriver, that product might not be able to perform its intended task. Hardness is a CTQ characteristic. Select critical processes. What qualifies a process as critical? If something goes wrong with that process, it will probably have a sizable impact on at least one CTQ characteristic. Critical processes are often indicated with a star on the control plan. Determine if machines can calculate SPC by themselves. Many modern pieces of equipment collect and analyze data, and then issue an alert when they get out of control. However, this is very uncommon in China, so let's assume this is not the case. It means you will need to carry out steps 4 and 5. Gather data and process knowledge of what impacts the output of the process. For example, the variables that might affect the output of a gluing process are listed below. Process input glue, process settings cycle time fixture, environment outside temperature, humidity, etc. Based on this, you might conclude that the viscosity of the glue and the ambient humidity are two variables that need controlling. But how can you get that information? It often comes from engineers, chemists, physicians, etc. But it can also come from operators who have been working on that process for some time and may have noticed some cause and effect relationships. Control independent variables that have a sizable impact on the process output. There are two ways you can ensure that your production does not deviate too much. First, gather data on the variables you identified previously on a regular basis, such as 5 random samples every 4 hours. Second, teach the production operators and leaders necessary calculations and how to plot them on a chart such as dot on the XBAR chart, the most popular tool. For simplicity, we tend to set a goal for the Process Capability Index, CPK, and let operators plot the evolution of that index over time. Look for ways to reduce variation. Now that you have made variations visible, the next step is to find ways to reduce it. If you use statistical process control charts, ideally it looks somewhat like this. As long as the CPK index is within the control limits, engineers and production leaders are encouraged to test different approaches. A CPK target of 1.0 is often attainable within a few weeks. 1.33 is more challenging. 1.66 is much harder. If necessary, you can use another statistical technique called design of experiments, though, to help you get close to the optimal values for variables that impact your process output. But be prepared, there are several available approaches here, and it can get relatively complex. Keep it up in the long term. Let's say you manage to reduce variation. Set a new target and keep controlling the key variables. If your process characteristics drift in one way or another, your statistical process control system will alert you. Otherwise, don't tamper with the process. Constant little adjustments will mechanically make the process unstable in statistical terms. Thank you for watching. Subscribe more such